We're going to add a layer onto that, what we were doing yesterday with the descriptions of how would you move in order to match different things. We're going to look at how are they related to one another. So let's consider, see if I can get these drawn. Let's consider three graphs or three plots here. Let's consider this first one as a displacement over a distance over time. Okay, and let's just take something fairly simple. Like a line. This is a displacement over time. How do you, you might want these in your notes, yeah, in the back section. These are the motion graphs. How do we know how fast that motion is? The motion that represents is, Owen?
The slope.
The slope, right? That tells us how fast. So if we had three lines, we could figure out which one is fastest pretty easily. Well, let's look at it further. If we wanted to find the slope, we'd pick 2 points. I'm not going to put in numbers here. And we draw our lines. That's not quite perfect. That's okay. And we take the rise over the run. Well, the rise here is a distance, however far we moved, right? The run is the time that it took. And if we found the slope, that would be the rise over the run, the distance over the time. Well, what do we get when we divide a distance by a time?
Distance by time.
That's a speed. That's a velocity. So not only does the relative slope of this tell us which one's faster, if we find the slope, it is actually the speed. Okay, so let's look at this. Let's look at just the blue parts here. Redraw that quick. So let's write down a rule before we go any further. Rule 1. The slope of a distance or displacement versus time plot is the velocity. Ignore me. Okay, that's important. So if you look at these and you can identify the slope, you know what the velocity is. What does the slope of this look like? What does the slope look like?
It looks like...
Is it positive, negative, or zero slope? It's a positive slope. Is the slope changing or constant? Constant, because it's a straight line, right?
Yes.
So that means the velocity, we don't have numbers here, so we're not going to worry about the number part of this, but that means the velocity will be a constant positive. So if we go down and now do a velocity versus time graph, how do we draw a positive constant?
I have a question.
Before we get there, how do we draw a positive constant? Sean?
From what answer we were doing the other day, positive would be below line.
That line's 0, right? Where is positive?
More positive as it moves forward.
No, I'm saying positive.
Well, then it would be above the line.
It would be above the line. What does a constant mean?
Above the line and straight line.
Not only a straight line, how else could we describe it?
Flat.
Flat. Positive and flat. We aren't really talking about, so in this case, we're moving a little bit beyond the motion relative to the wall. So we're moving in a positive direction and it's flat when we relate these. You're right when you're describing your motion that it feels backwards. So the velocity that goes along with our, let's see if I can get it, goes along with our displacement graph looks just like this. Now what was your question, Owen?
So like if a line, like for like the distance to time plot, so if a line if they're both like that, could you say like the first line is constant and that changes direction, then it
So how would we write that? So we've kind of got the first thing, and if I lined this up by time, that would be even better. So for that first amount of time, I've got a positive constant slope up there. What does the slope of this portion look like? Negative, and what else can we describe? Constant negative.
away from the wall.
Well, again, this we're kind of getting away from, from the away from the wall or towards the wall, and we're just relating one graph to another. What would a negative constant look like? What does a constant look like?
Straight line.
Not just a straight line,
Flat line.
a flat line, and it's negative, so it's below our zero. So the second half of this would go down here and continue, and then we would sort of have a dash line. We're going to kind of forget about that too. That's another layer of complexity that we don't really want to get to.
Wouldn't like having a distance over time, having it go like that, wouldn't the velocity versus time?
It's not really a gradual, you're saying a gradual. There would certainly be a connection, but look how abrupt that is. Physically, we can't just, that's just a change like, moment. Physically, that can't really happen. And so that's this portion, it sort of just changes immediately. Not really physically possible, but for our purposes, we're going to kind of just fudge that and say, yes, something happened and it suddenly changed. Okay, let's look at velocity and time, and let's look at another graph here. If we had a velocity graph like this, so our velocity starts at 0 and then it's increasing. Let's take a look at the slope there too. We pick out 2 points. The rise part would be whatever that velocity is minus that, so let's say v2 minus v1. And then we'd have some amount of time, we'll just call it t. So if we found the slope of this, we'd have an expression like that. That would be the slope of this line. What other characteristic do we have that's like?
Acceleration.
That's acceleration. That's our second rule. The slope of a velocity versus time plot is acceleration. Since we only have a couple minutes left and I want to get you a minute or two, I want to at least introduce this even if we change future plans. This last worksheet that I'll hand out today asks you to look at the displacement versus time plots, which are on the left, and say each of these matches one of the velocity versus time plots in the middle. So you'll match letter A with one of these, write it down there, and then these velocity plots match up with one of these acceleration plots. Now here's the trick. You only use the letters in the first column once, and you only use the letters in the middle column once. The ones in the third column can be reused as needed. Right, and you can could reuse every single one. It could be the same answer for all of them, if that's how it turns out. But the ones on the left match up with only one in the middle.